um, I'm David Salinas. So I'm gonna present Syne Tune, which is a new library for large-scale hyperparameter tuning and reproducible research. This is joint work with Matthias Ziger, Aaron Klein, Martin Witztuba, Valerie Pernet, and Cedric Archambault. An overview of what I'm going to talk today. I'm gonna talk a bit about hyperparameter optimization, just to mention like the different topic that the library currently cover, so that we are all on the same page. Then I'll discuss what like the library, so how one can use it, and show like different HPM methods and schedulers that are supported. And one of the most important aspects, I guess, is I'll showcase how you can easily change how you execute trial, like locally on the cloud on simulation. That would be hopefully more clear when I get there. And then some experiment results, one use case, and then I'll show you a quick demo. If you have any question during the talk, please feel free to interrupt and ask it. You can also, of course, ask it at the end. So hyperparameter optimization. So we all know what it's about. So tuning all those knobs. So formally, we have a hyperparameter x and like a function that takes this hyperparameter, and that's an objective that we want to minimize. So for instance, to train a neural network, so there is some hyperparameter and we want to find the best one. So we want to find this optimization problem with the caveat that evaluating f is expensive, so probably we don't have gradients. So we are okay approximating the solution as fast as possible. And yeah, so the basic methods are, well, grid search or random search, so they're embarrassingly parallel, but say not so good at exploiting. So there are like lots of key techniques to speed up random search. And I'm just mentioning those because those are, we did some effort in having a coverage on those techniques. Of course, they are like all techniques, but so right. So Bayesian optimization is like, well, rather than random sampling, you have a surrogate that exploits past evaluations. Multi-fidelity, I'm going to talk slightly more as like if you have access to intermediate evaluations, so for instance, result at every epoch, you just cut out configuration that don't perform so well. Asynchronous distributed optimization is like yet another technique that can be also combined with those two. So where you will run different multiple workers that evaluate configuration in parallel, and you have something that's asynchronous, so you don't wait until they're all done to schedule a new wave of configuration. And transfer learning is when you exploit information from previous HPO runs. So for instance, let's say you run HPO every week or something. It's a bit sad to start from scratch because you already have lots of information, and that encapsulate those type of techniques. So I think Bayesian, I'm just gonna talk briefly about this one and this one. I guess the other people are familiar in the talk, so in the audience. So multi-fidelity is you just run rather than running all configuration for a full budget. You run it for like a small budget, and then you check and perhaps you discard like the bottom half, and you continue by doubling the budget and so on and so forth until you have only one configuration. So this would be successful halving. There have been like a lot of follow-up. So Hyperband that does I guess some extension. So like Bob has also been proposed, because here you will just sample configuration random, so it's a bit inefficient, so that you combine this type of early stopping with like a model base that can find configuration around the spaces that are good. Asha and Monster, I'm going to talk slightly about those. So it's basically Asha is an asynchronous extension of Hyperband in the sense that you don't, Hyperband will basically wait here that all things are done, then take a decision and let continue. The configuration continue, but that can be wasteful because some configuration may be much slower. And Mobster is an extension as well, so it's asynchronous, and it also has a model to avoid the random search issues. So, right, so like, I mean, Asha and Mobster are two instance of like asynchronous optimizers, if you will. So what does it mean is like essentially rather than waiting for configuration to finish, you just, whenever you have a result, you take a decision. So maybe you cut the configuration and you schedule something new, but there's a key thing if you don't wait. And you can get large performance gain. So here I'm illustrating asynchronous optimization. So I hope you excuse me, like I realize by compiling my slide that this should be Asha because it's asynchronous, but well, let's look at how it will work. So like here you have like 4 workers that launch configuration, and we see their progress over time, and so on and so forth until the search is done. And asynchronous is really like basically you see here the 4 workers, but whenever one is done, we just schedule something immediately. And the time for synchronization becomes so large that you just lose a lot of performance. Right. So right, so that's all basically the background that we need to talk about the library. So so this library, the key features are I'll say like the coverage of baseline. So you have I'll talk about that later on as well, but you have a lot of methods from single fidelity methods to asynchronous and synchronous multi-fidelity methods, such as Hyperband, Bob, Asha, Mobster. One very important point is that it's backend agnostic. So in a sense, you just need a code change to run the same tuning on your machine or on the cloud or with simulations, which basically makes it much easier to compare different setups. We also have advanced methods and use cases, so like transfer learning, as I mentioned, constraint optimization, where you say you want to find configurations such that you have a constraint that is not violated, such as below a certain latency or above a fairness level, for instance. We also have support for multi-objective optimization, where you have more than one objective, and lots of tools for doing benchmark that basically allows you to plug and play with all those components and simulate efficiently what result you would have. So let's see first how you could kind of use it if you want to tune a function. So like basically as a user, so you define your config space, so the range of parameters you're looking for. You then create this tuner object, and that you configure by saying what you're going to run, how you're going to run. So I'll talk about each of those components just after. What optimizer you're using or scheduler, how long you run for, how many workers you have in parallel, and basically that's it. So let's see not just how the I'll show you how the tuner loop works so that we have a high-level view of of this component. Then I'll discuss like as a user, how would you provide this training script? What do you do to report what do you need to do to report your results? Then how you can use a different scheduler, so basically it's just passing a different object, and how you can choose that rather than evaluating on the machine, you evaluate on the cloud or with simulation. Okay, so the tuner loop is something like that. So while you have not reached your stopping criterion, if there is a worker that is free, you ask your HPO method, please suggest me something. You then send it to the backend that has the responsibility of running this thing. And also you query regularly if there are new results. As soon as there is a new result, you communicate it to the scheduler, and it can take a decision, for instance, to stop if it's a bad configuration. So it's a simplified view, but that's basically the main idea of how it works. So yeah, the tuner loops is basically such as until the best configuration until the stopping criterion is met. The schedulers is like the NHP algorithm, so it has to suggest when new configuration when there is some space in your backend, and when there is a result, it needs to react to it. There is like a couple of things that more than a scheduler can do, but for the sake of simplicity, let's go with this one. And the trial backend is the component that is responsible for evaluating something, stopping something, and doing the bookkeeping of results. Like at any time needs to be able to tell you there's a new result, for instance. Okay, so let's see. So let's see now how, like, a training script. So how will it look like? So that's I mean, I will assume that basically you have some training script that takes some hyperparameters, command line arguments, and the only thing that you need to do is like those 2 lines here is like you need to report results as soon as you have them. So that's basically just this line. I mean, you need to create the object, but also pass those results. One thing to say is that we log also over metrics that can be tuned as well. So for instance, with multi-objective optimizers. So for instance, in runtime, you always know it. And we also detect like the dollar cost so if you run on a cloud machine, at any time we report, that you spend $2, $3, and so on and so forth. So in case you want to do multi-objective optimization. Okay, so using a different scheduler is like here we're using Asha. Well, I mean, you just pass a different object, right? Here, like that's how, for instance, you can use Monster that has a GP to avoid the random search as Asha does, and that's about it. And so, as I said, we try to have a good coverage of baselines. So that's the list of the ones that are currently supported. So the first group of methods is like single fidelity methods, so to say, that don't stop when they see a bad result. It just evaluates all configuration fully. Then this group is like asynchronous multi-fidelity methods. So you have Asha, Mobster, Bob, also median stopping rule. And you, as synchronous methods, you have like, synchronous hyperband. So basically hyperband, like Bob and PBT. For transfer learning methods, we have like a couple of them. So I'll talk about that in the results. And also the last category is a bit like, MISC. So it's like multi-objective and constraint. I guess we probably had more multi-objective methods in the future. So I should note also that we have wrappers, so any schedulers in Tune can run through those. So technically, you will also have other methods that I don't mention there. And I mean yours. So that's the next slide. So if to add a method is rather easy, you basically need to say what you suggest when there is space, and when you do, and what you do when there is a new result. So here, that's just a simple example that is in our code base where, I mean, to suggest you just sample something new, but you could use a GP there. And when there is a result, you do something funny. So if the result is worse than 80% of what you observe, for this budget, you stop it. Otherwise, you continue. But yeah, you could do anything you want, basically. Okay, so I talk about changing trial execution. I'll try to motivate a bit what maybe why it's important. But so basically, when you want to run a tuning, an HPO job, there can be many scenarios, right? Maybe you want to run on your machine or like on your local cluster or on the cloud. As an endpoint, if you want to do something for inference, there's just like a lot of possibilities. Like this is like basically where there could be also how, right? Like so like I'm just showing Python program, but maybe you just want to tune like a JVM program or whatever. So basically, we made sure that the design is flexible so that you could add like any type of backend, basically. And so we support like 3 for that at the moment, 3 main ones. So the first one, like that I already talked about, is like the so-called local backend. So you just evaluate on your machine. So here you have 4 workers. So like you have different sub-processes that runs concurrently on your machine. If you have multiple GPU, you have an option so that is basically assigned to the least busy GPU. This solution only works as like, I mean, if you want to run 100 workers, you know, in parallel, like a single machine is not going to cut it. So we also have a backend where you would rather use a separate machine for each configuration. And for that, basically, we provide wrapper with SageMaker. So, I mean, it's like basically SageMaker, if you have never heard of it, maybe I'll take 2 seconds explaining it. So it's a AWS, like an AWS offering for machine learning. And among the things that it does, it provides a lot of wrappers so that you can launch a training job with, like, for instance, custom containers that are built for, you know, PyTorch, Hugging Face, XGBoost or whatever, and that you just access with one class. And so then it gives you a container that is optimized for CUDA or like or whatever. So like it will automatically know if it's a CPU, GPU machine and fetch right image, which you can also configure by giving the, you know, for instance, a PyTorch version. And I guess like the advantages is that, for instance, you can increase the instance count, and that will enable distributed training, or you can with one line just, you know, use a spot instance so that then it becomes quite cheaper. Okay, and the last one that's maybe last but not least is a backend when you want to do simulation from lookup tables. So this is maybe the bit that is very important, I guess, for research, because essentially it allows you to run simulations, or I'll show some results about that later, very fast. And so one thing to note is that it's, I'd say it's not entirely trivial how, I mean, like the algorithm is pretty simple, but it's like some implementation effort to handle, you know, asynchronous distributed optimization if you have lookup tables. Because if you do the naive strategy where you just, whenever you have a configuration, you look in your table, then you will need to sleep for the amount of time that is recorded, because you don't want to mess up like the order that would have happened if you run the experiment for real. Whereas like in this component, we just have an event queue essentially, and we just update the time very fast while making sure that it's consistent to like what you would have if you would have run the true thing. And right, and so as I said, it's easy to add other backends. Yeah, you could easily add others. So for instance, Slurm, or I don't know. This one shows that, yeah, I mean, you can easily get results from the past tuning, but maybe this one I'll skip because I'll talk about that in the demo. And this one as well, like, so yeah, so whenever you run something, there's like a folder that's created with results, the state of the tuner, if you want to resume it later or inspect what was, I don't know, what was the parameters of your methods, and some metadata. Okay. So let's see some experimental results and one use case. So first I'll just describe the experiment setup that we're considering. Then I'll show some method comparisons, and then I'll show use case where we tune hardware configuration with multi-objective optimization. Okay, so for the experiment setup and method comparison, we are using comparison of 12 black boxes from 3 families of tabular benchmarks. Yeah, so you have a bunch of statistics. I guess the message is that, well, they're like a bunch of tasks, but also that such spaces are maybe quite different. So like you have master1, which is this, categorical search space, like fully categorical search space, and you have like FCNet, where like the search space is, there are some categorical stuff, but also some parameters which are kind of finite range. So they're not one hot encoded in the GP, but like you use a kernel with those values, right? Appropriate kernel, and LCBench, which is slightly different from the other also because it's like continuous search spaces. You don't have all the configuration, so we use a surrogate on top of that, which I'll talk about later. Right, okay, so we have these 12 boxes, and then we also have 12 methods. So we have a bunch of single fidelity. I mean, that's basically from the table I've shown earlier. Then we have multi-fidelity methods that I talked about already. And so transfer learning methods, we have zero-shot configuration, essentially. So it's an approach that just build a list of configuration that was good, from previous ranks on previous tasks, and then just play it and like sequentially. We have Asha with bounding box, that's a baseline that was proposed. Where essentially you pick all the best configurations that you had in your past tasks, you compute a bounding box, you restrict your search space, and you run Asha on top of that. And last variant where we run Asha, and rather than sampling randomly, we use a quantile-based surrogate that was proposed in this paper. So in all experiments, we simulate 30 seeds for all methods and black box combination, and we run with 4 workers. So before showing the result, I'm going to talk about the simulation and mention why maybe it's important. So first, why go through all this trouble about asynchronous distributed HPO? So that's the answer is in this figure, because it has a massive impact on performance. So so here, for instance, if you look at the time it takes to reach like a 29% error for this black box, with 2 workers, you have basically a 2 times speed up. With 4, it's around 3, and 8 around 4. But so you have a massive. So it's not perfect scaling, but it's a pretty good one. And this is very often used to avoid large workload time. So that's so it's quite important to be able to benchmark methods and in this setup. Let's say asynchronous distributed HPO is important. The plot on the right shows what you have if you run Syne Tune by using the simulator. So that's this dash simul for Asha. So I forgot to mention stopping and promotion. So let's say it's 2 variants of Asha. If you know it let's say it's just variant of Asha. So so the dash simul is like the result you obtain if you run a simulation with a Syne Tune, and the dash local is the result you obtain if you run like the same experiment but by putting workers asleep, which will be exactly the same as if you would have run it in real life, right? And what you can see is that there is like basically like no difference. So there is like a tiny amount of difference because I mean there are like, I guess, super OS effects, but so it won't change any analysis that you make on those results. But one thing is that, so if you put your worker to sleep, then the workload time that you will pay is like this 20,000, right? So I don't know, like maybe 6 or 7 hours. But when you run the simulation, I'm going to show you in the demo, it takes like 5 seconds or something. So that's a really, you know, much faster to get kind of results. And basically, you just pay the time for, you know, like your optimizer decision. So for instance, if it's a GP, right, that's the time that you're going to pay, and you're going to measure new results, but that's basically it. So to get fast simulation, there is another thing also. It's like, so we made sure that the tabular black boxes are kind of efficient. So we have a unified format that we optimize for this use case. And here you see the performance on the 3 benchmark families. When you, I mean, baseline is like basically the best code you can find. So that's a time in seconds, for instance, it takes to load like a benchmark of this family compared to Syne Tune. And on the right column, you have the time it takes to with all the fidelities of one configuration. And I mean, not everywhere. So for instance, XCbench is very efficient, you know, at providing this lookup, but like Orize most of the time, it's like I guess the implementation is like every author, you know, we implement something, maybe it's not efficient, and this can play a big role. And so I guess this is often neglected because you say, you know, I mean, it's fine, like the 0.2 seconds, for instance, for master 1, I'm saving 2 hours, you know, so that's a fair point. But on the other hand, when you run the simulation, you actually do need a lot of query or lookups, right? Like so for instance, if you run for FCNet, like if you run 1 schedulers for like 30 seed of 1 schedulers, like, you know, experiments was around 600,000 lookups, and that corresponds to like 5 minutes, you know, like but if you use some like the best public implementation is 2 days. And so that's something that can also help to, you know, get more results and get like this positive loop for research. Okay, so let's see now some results. So I'm going to first show results on 2 tasks, with and without transfer learning, and then I will show some aggregate results. So we have 12 tasks. So we just picked 2 that somehow tell the overall story. So here you see all the methods and their performance over time. So in a sense, it confirmed what we kind of know. So like that, you know, this TPE evolutionary algorithm or GPs, they outperform like random search slightly because they can do exploitation. That multi-fidelity are very efficient, like here, like the performance is pretty large. I guess perhaps like things are new. So for instance, I'm not sure like medium stopping rule has ever been compared to hyperparameter. I don't know, like maybe, I don't know, I've not seen it. But also it's a comparison, like, you know, in a asynchronous distributed setup. That's also something that is a bit new. And this is I should have said, so that's, I mean, the caption says it, but this is a task from FCNet, so it's nice, and this is a task from NASTO 1 CFAR 100. Okay, so when you compare with transfer learning, so here we just compare with random search and ASHA, so it's the same result from random search and ASHA, but we just we just select those methods for that, so that to not have not to overload the plot. So so transfer learning methods, they work pretty well. So that's just a confirmation about, I guess, what we know. Like probably, though, it's like I'm not. I think I've not seen so much like a comparison where you can compare transfer learning method in a distributed asynchronous setup. So then we show like aggregate results. So there are obtained by running all method property sets, then taking the mean performance, and then compute the ranking of the methods in 10 equidistant time steps, and then averaging these numbers across time and benchmark. So it's normalized rank. So 0 means that you are the first method always, and 1 that you are the worst always. And it's, as I said, it's kind of confirm what we saw in the previous plot. So for the single fidelity methods, all methods that can exploit information are slightly better than random search. GP seems to be the best in this case. I guess median stopping rule is like always worse than the other approaches. And transfer learning gives a big boost, although like there of course comes you need like offline evaluation, which you don't always have. So that's it for like the experimental results. So then I said I will talk about one use case. So this use case is about finding the hardware or like the type of machine that you use when you query a black box function. So and the reason for looking at this use case is like hardware or machine type. It's often that constant, but it has a massive effect on cost and runtime, and it requires an expertise to be set correctly, right? Like so, for instance, if you use AWS, maybe there are like 100 of different machines. You know which GPU you pick. You know it's very hard. So like new machines get added all the time, and the claim is that essentially like the default choices are often pretty bad. So this plot, for instance, shows like over multiple seeds, so that's why you see several dots, the time and cost it takes to train a ResNet with a bunch of machines on AWS. And so that's our logarithmic axis. So it's like massive difference. And this is for ResNet. You know, if you will do a BERT, you'll have a completely different story, or if you like a model on XGBoost. So it's virtually impossible to know which instance are going to be the best, you know, upfront. So typically what you would like is like an algorithm that can find the best instances. So of course there is not a best single instance, because so for instance here there is one that is I mean there is one that is the fastest here. No, that's actually sorry, this one is the fastest, and this one is among the optimal one, the cheapest, but it may be that you actually want something in between, right? And so the only thing that like you have to return like a set of solutions, so like the title font, so the older instance that are in the bottom left. So just to describe the method that is currently implemented in Syne Tune, so it's called Moisha. So I mean, first, if you are successful halving hyperband or Asha, well, you can realize that the only thing you need to do is to sort configuration at a given time or budget, and that's the only thing that you need to do, right? So it doesn't work in multiple objective out of the box, because you don't really know how to sort, you know, multiple objectives. But if you extend to multiple objective sorts, then you have an easy extension to like multiple objective, or you know, hyperband or Asha. So I guess in one of our paper we call it Moisha, but it was proposed by other authors as well. And well, so like the question now is like, which multi-objective sort do you pick? I mean, that could be a long discussion, but I just want to advertise the one that is in those 3 papers, and why linear scalarization or like I would say simple scalarization are usually pretty bad. So let's say if you have like an objective F1 and F2, what people often do in practice is to just sum them up, and that's your new objective. So you're back to the single objective case. So let's see what it will do. For instance, so here we have a bunch of points, and we show their like a bunch of configuration, and we show their objectives F1 and F2. So if you do a linear scalarization, and here I'm plotting like the value that you will obtain, you'll obtain something like that. So you only be able to select those points, and maybe you see it mathematically, but you know, it's the level set. It's of like linear function can never ever reach a point in the middle, right? So that's a bit of a pity, right? And it's not so much of like a say a far-fetched example to have like a set of optimal solution that is concave. So for instance, if you look here, like that was a concave shape, right? That does happen in practice. So yeah, so it's not really good in sterilization. So so you can do much better. So I mean, it's one of the approaches. There are also approaches that are valid, but so one thing that you could do rather is that since you know you want to ultimately you want to select the Pareto front, you could compute the Pareto front from your set of objectives, and you say, okay, those guys they get the top priority. Maybe you select it at random, like to break the tie. Then you remove them and you recurse, right? So those guys will get the next higher priorities, and those guys and so on. And if you do this strategy, here I'm showing the priority again in color, you get basically the optimal thing that you would expect. So it seems like a good idea to do with I mean, Asha. And so we I mean, we studied this use case where the black box is we want to fine-tune BERT, and we have two objectives: the latency and test error. And the hyperparameters are, you know, some model hyperparameter, but also like the instance type. So you know, the type of machine that we use, and there we can. I mean, basically with this this property that you select the Pareto front, we can get a good hypervolume by also stopping bad configuration early. And I guess maybe like the same point is not so much about, well, I mean, like it's really about the fact that you can do it, right? Like, so that's because we have this different this modular API like for the backend, and one, like, so for instance for the cloud backend you can just make the machine type a hyperparameter and search for it, which I guess you don't have in a, you know, other frameworks. Okay, so right, so I'm almost at the demo if I still have time. So where to go from here? So you can check out our documentation. Like we have a bunch of examples on how to run all the methods, how to tune the instance type, or like show results and all those type of things. Right, I mean, if you have any question or feature request, please send us an issue. And right, okay. And the demo, maybe I can do it in 2 minutes. So just like things essentially that I skim through, but let's just see how that ends up. I'm not sure if it's the right version, but that should be it. Right. So that's how you will run tuning locally. So that's the thing. So if you do that, well, you have a bunch of information. But I mean, maybe like one important one is like your results are stored into this folder. After a while, that like the search will be over and it shows you a summary. If you look there, there will be, say, like some results, and those contain also the log of your trials. And yeah, you can easily plot the results and log your results by doing using this util. Okay, but I guess maybe something else more. I don't know if it's more exciting for research, but it's like the simulation backend. So I said it was fast and all, but like let's see how it performs. So here I'm just using one of the tabular benchmark that we have. And okay, so I launched the tuning, and yeah, I guess it will be over because I think it takes just 1 second or something. And you have the performance over time that you achieved. And well, okay, so maybe I'm going a bit fast. So like this experiment contains a table, like a data frame of like everything, so that you can use for extra analysis. So here, for instance, I'm generating a similar plots to what I had in the talk, where I show the trial over time. Or I mean, you can see that's you know, like the stopping decision with this red dot, and that things are asynchronous with two workers. And maybe the last thing is that I said it was at the end, it was pretty fast to run, or let's say to run things. So let's say I run 5 seeds. So I'm just running this tuning 5 times, and I mean, it took 8 seconds, but it's I don't know how many, but it's like maybe 100,000 of evaluations to look at or something like that. And the last thing before I stop that I wanted to show is that for this this simulator backend, you can also put a surrogate pretty easily. So here we use LC-bench. So as I say, the LC-bench, it doesn't have all the possible configurations. So you have to do something because the method may sample something that don't exist. And oops, sorry. And so here, like it shows like how you can build a surrogate. So essentially, there is a scikit-learn model that is learned on the fly on the data of the benchmark. You can technically here it could be any scikit-learn estimator that you can configure, and then you can run it, and it will work because although it's gonna sample things that don't exist, it's gonna use this surrogate that you gave. So it's a KNN, but it could be XGBoost or whatever. And yeah, then you get the result as if nothing has, I mean, as if all the data were there. So I guess it can also be useful, like to see the the effect of different surrogates. I don't know, a bunch of other stuff. So, well, okay, yeah, that's it. So thanks a lot for your attention. Let me know if you have any question or